All right, so in this last lecture, I introduced to you, let's say, the basic concepts of parallel computing. We talked about how you have to, let's say, what the hardware is and how you map software onto hardware. Let's say how the operating system splits things into processes, that is programs, and then within each process there might be multiple threads, for example, and so on and so forth. So what I would like to talk about today is when you want to parallelize a code on a single processor, how that works, how you would structure your code, and how you have to think about this. And ultimately, I think what you will notice is, if you want to work on parallelization, is that it takes a certain mindset that you have to change the way you think about things to make this successful. I can't teach you this right away, but I can give you, let's say, the ideas, the concepts that you can use to apply this. So let me start with this. This is lecture 40, parallelization on a single shared memory machine, and then we will come back in the next lecture where I'm going to talk about parallelization on multiple machines that do not share a memory space. So I would like to start with an example, and that is an example that you have seen multiple times before if you went through the tutorial programs of deal.II, namely a function like the setup system function that we have in many of these tutorial programs. So setup system basically always looks like this. So the first thing is you call DOF handler.distribute DOFs. That means you enumerate all of the degrees of freedom that live on a mesh, for example. The next thing you would do is, for all of these degrees of freedom, you find out which of these are hanging nodes, for example, and you construct this constraints object, the constraint matrix that we use to describe these hanging nodes. Then you build a sparsity pattern, and you might associate a matrix with it. And then, for example, also you might want to interpolate boundary values. This is something that in some of the other programs we've actually done. This last call to interpolate boundary values we've done in the assemble system function, but you could do it here if you wanted to. So one of the things that you might notice is that the order of these three operations does not really matter, right? The computation of this sparsity pattern does not depend on the hanging nodes that we have just computed. And conversely, the computation of the hanging nodes does not depend on the sparsity pattern that we have. So if we wanted to, we could switch these two around. And the same thing is true for the computation of boundary values, where we interpolate the boundary values in all of the nodes around the perimeter of the domain. That too, this operation could be switched with any of the other two. So in other words, these three operations here are all independent of each other, and we could reorder them however we would like to do. On the other hand, all three of these actually depend on the distribution of the degrees of freedom on this mesh. Because if you want to find out the constraints of hanging nodes, you need to know what is the number of a degree of freedom that lives on a hanging node, for example. Likewise, if you want to build a sparsity pattern, you need to know what is the number of this degree of freedom on a particular vertex that couples with the degree of freedom on a neighboring vertex. So you need to know their numbering. So all of these three operations that I have enumerated here with 1, 2, and 3, they do depend on this operation here, and I can only run them after that. But because they don't depend on each other, and because they all write into separate data structures, so the first one will write into the constraint matrix data structure, the second one is going to write into a sparsity pattern data structure, and the interpolate boundary values object is going to write into a map from unsigned int to double, or from a map from global DOF index to double. All of these write into different data structures, and so in other words, I could run them at the same time if I wanted to. Let's say if I have a machine with 4 cores, I could run these 3 functions at the same time. And so let me show you real quick how this works. I introduced the concept of threads to you in the last lecture. So I could call, for example, the rather low-level function pthread_create. So pthread stands, the P stands for POSIX. POSIX is the standard for many of the operating system functions on Linux systems, or on all kinds of Unix systems. So I could call pthread create with this particular function and a list of arguments that I somehow need to pass. And what it's going to do is it's going to start a new thread and it's going to execute this function on the thread. And while it's doing this, on the mother thread, I call pthread create again with the function make sparsity pattern, and then a third time with interpolate boundary values. So in other words, what I have done is I have the main thread of my process now, and I also have 3 new threads that are doing something else. So at this point, if there was only a main thread at the beginning, my process will consist of 4 different threads. Now, before I leave this function here, I have to wait for these 3 threads to terminate. And there is a function that is called pthread join that I would call for each one of these 3 threads. I should note that this is not the real syntax that we use for pthread create. I'm going to show you an example later on. Pthread create has a rather awkward interface, and it does not quite look this way. But the idea, I think you get. If you want to look at the exact syntax of pthread create, type man pthread create on the command line to get the manual page of this function, and it's going to show you the syntax. So the point of this is that what I've just done is I have created 3 new threads that will be running concurrently with the main thread and will be computing things in parallel at the same time. Now, for pthread create, there are a number of syntactic problems. There are other problems that I'm going to come back later, but let's say syntactic, using pthread create is just a really awkward interface. It does not allow easily to pass arguments. I'm going to show you an example in a minute where you see the actual syntax of pthread create. It essentially just gives a void pointer to the function that we call, and somehow through this void pointer you would have to pass the arguments. That's just really awkward to do. The same thing is true for return values. If a function returns something, you might want to get at the return value after the thread has terminated. So in other words, after this function has finished, you would want to get back at the value that this function returned. That too is something that is very difficult to do with pthread create. And I think as a general rule, pthread create and any of these pthread functions is very low level. It is not really intended to be used in applications programs, let's say at the level that you will probably be programming at. It is essentially just an interface that you can use to get the operating system to create a new thread. And typically, you would hide this sort of stuff behind a layer of code that makes it easier to use. So let me show you how we do this in deal.II. So in deal.II, we have a set of functions that are living in a namespace threads. And this function, for example, would be called new thread. You give it a pointer to a function that you want to call on this new thread, and then you would just enumerate all of the arguments here. And what new thread returns to you, so in this case it really returns something, is an object of type threads : thread, and then in angle brackets you would list the return type of this function. So in the case of make hanging node constraints, it does not return anything at all. In that case, the object that it returns would be of type threads, thread void. If you had a function, for example, that would return an integer, then the correct type that is being returned by new thread would be threads : thread int, for example. So with the syntax, this is actual syntax that you can use here, with the exception, of course, of the ... which you need to fill in somehow. So with the syntax, then you get these 3 thread objects, and you can write thread1.join, for example. Join is the operation. I think historically people have thought of creating a thread as forking. So you have your main thread that keeps working, and then you fork off a separate thread that is going to work on something else. And at one point you have to have a junction where these two come together. So the call thread1.join waits for the other thread to finish. So the call to join will simply halt the main thread until the newly created thread has finished. So With this interface to new thread, there are still a number of other problems that I would like to talk about. Namely, it is expensive to create threads. For an operating system, to create a thread essentially means you have to create all sorts of data structures in the operating system. And among other things, you have to create a stack for this new thread. That means you have to allocate memory, you have to set up all of the data structures that come with the thread, and so on and so forth. So it's an expensive process, and of course terminating a thread is then expensive as well, because you have to tear down these data structures, release memory, and so on and so forth. That's a problem that I think could be overcome. The bigger problem that you have when you explicitly use threads is that I talked to you earlier that when you want to have your program scale on processors, that what you need to achieve is that the number of threads matches the number of virtual cores that you have. So in the example that I showed you, I created 3 new threads for a total of 4 threads. But what happens if I have only 1 core on my machine? That I know that doesn't happen anymore today. Even my cell phone has more cores, but pretend for a second that I have only 1 core. So in that case, I have 4 threads that need to share this 1 core. And what's going to happen is that the operating system scheduler is going to say, okay, well, I have these 4 threads that all want to run on this 1 core. What I'm going to do is for a millisecond, I run thread number 1, and then for the next millisecond, I'm going to run thread number 2, and for this 3rd millisecond, I'm going to run thread number 3, and so on and so forth, round robin. That is not an efficient way of doing it. It means that I have to terminate every thread every once in a while and switch to another thread. That means that the cache will go cold, because these threads, of course, want to read and write different pieces of memory, and so on and so forth. So it is not efficient if you have too many threads, let's say more threads than you have cores. But of course, it is equally inefficient if you don't have enough threads. So let's say in this example, I created 3 threads plus the main thread, which actually doesn't do anything anymore once these 3 are running. But I have 4 threads in total. What if my machine has 64 cores, for example? Several of my machines in my lab have 64 cores, which I'm sure in a few years will be a fairly small number. Out of these 64 cores, when I run this program, 60 will be idle. There is nothing for them to do. So with explicit threads, it's just very difficult to match the number of threads to the number of cores that I have, because I just create them without any knowledge of how many cores I have in this system, in my machine. Typically, I just create threads because I can see that these functions can be run independently in parallel. But I need to somehow match this to the actual machine that I have in order to make it efficient. Another problem that I have in this context is that it's just very difficult to make a large number of threads. So if you have a machine with 64 cores, or in a few years maybe one with 256, when you look at your functions, it's you can often identify certain pieces of code that can be run in parallel, like the 3 pieces that I just showed you here in this example. But when you want to drive this to higher and higher levels, let's say if I really wanted to make this scale on a machine with 256 cores, for example, where am I going to find these levels of parallelism? Typically, if you look at your program, if you look at any, let's say step 6, for example, you will find that there's that I can identify functions that can be run in parallel, for example, in setup system. But none of the other functions can do this, because typically what you have is that every call to a function is dependent on the previous one. And that means I cannot run them in parallel. I first have to wait for the first one to finish before I can call the next one. Let's say, for example, in the solve system, I cannot call distribute, I cannot call hanging node constraints.distribute before I have actually finished solving the linear system. So these are the sort of constraints that you typically have to work with, and it's just not possible to, with explicit threads, to find enough opportunities for parallelism. The last point I want to make is that this sort of approach is difficult to make work if you have multiple levels of parallelism. So for example, let's say you know that your system has only 4 cores. In that case, you have parallelized your function setup system in such a way that it really produces the 3 threads plus the 4th thread that keeps running, the main thread. And you say, hooray, I've successfully matched my code to the underlying hardware. But what if you have identified, for example, that setup system can actually run in parallel with something else? Let's say, for example, you wanted to read some data file that describes material properties. So you identified the fact that you can run setup system in parallel to the function that reads these material properties. And you have created 2 threads, one that calls setup system and one that reads the material properties. In setup system, you don't typically know this. So if you have managed to match setup system to your hardware, then that only works if this is the only level of parallelism you have. But now you have a higher level where setup system is running in parallel to something else. And so in order to match this again to your hardware, you would have to somehow propagate this sort of information, how many threads you have already started. And that's just very difficult to do. How are you going to tell setup system that there are already other threads running? So these are just practical difficulties that make it awkward to really work with threads in an explicit way. I would say threads was something that we used until maybe 5 years ago, until the mid-2000s. But that we have better ways of matching what we actually want to work on to the hardware today, and I'll come back to this at a later point. One of the other things that I don't have on the slide here is I showed you how to run things in parallel with this new thread function here. Now, what this doesn't guarantee, of course, is that the 3 calls to make hanging node constraints, to make sparsity pattern, and to interpolate boundary values actually run the same amount of time. What's going to happen in practice, of course, is that one of them typically is done much faster. For example, my best guess is that interpolate boundary values will be finished much earlier than the other 2. And so once this thread is finished, I have only these 2 running, and the processor core, or the virtual core, that had been executing interpolate boundary values will be idle. So what are you going to do about this? Right? For a processor to be idle is always a loss of potential to do things in parallel. That's going to hit you in Amdahl's law, because you come to a point where only one thread is still working. That is part of the sequential component of what we have in Amdahl's law, part of what goes into this fraction. I think I called it S in the last lecture. So the goal always had to be that all the threads are busy all the time, and that's very difficult to achieve if you explicitly create threads. Okay, so that was a simple example of the setup system function. Let me show you a different example. So if you go to the assemble system function, for example, that is, you will find something that we call embarrassingly parallel. I showed the slide to my wife yesterday, and she was quite amused by the colorful words that computer scientists often use. I think I've gotten so used to the word embarrassingly parallel that I don't even think about this anymore, but it is true. It's a nice choice of words. Embarrassingly parallel essentially means that we have much more potential for parallelism than we have cores. So for assemble system, you remember that, of course, the main part of assemble system always looked like this. So we have a loop over all of the cells, and on every cell we reinitialize our FA values, and then we assemble local contributions, and we copy these local contributions into the global matrix and right-hand side vector. And if you think about this a little bit, of course, then you will realize that the assembly on one cell does not actually depend on the assembly on another cell. So we could be running the assembly on cells 1 and 2 in parallel, as well as on cells 3, 4, 5, and so on and so forth. So on, let's say, a typical computation today, I might have 100,000 cells, or on a large computation, many more. So if I wanted to, I could be creating 100,000 threads. And each one of them, on each thread, I'm going to assemble the local contribution on one cell and then copy it into a global matrix. I can do this like this. So if I wrote my function like this, assemble system would just have this loop over all of the cells. And on every cell, then I'm going to create a new thread that is going to call function assemble on one cell. Assemble on one cell is up here and is going to do the work that is necessary on one cell, including copying to the global matrix and right-hand side. That is something that I could do in principle. I will be able to utilize all of the virtual cores for the next 30 years that we will find in machines, because let's say if I have 100,000 cells, I could start 100,000 threads. It will take a long time for hardware manufacturers to come up with machines that have so many threads. The point is, in this case, that is not very efficient. I just have too many threads. That's the operating system will find itself busy switching between threads all the time rather than actually executing work. So maybe this is not the best way to do it. Here's an alternative where I don't quite create that many threads, but rather what I'm going to do is something like this. So this is maybe a little bit hard to read. So I have this function assemble, and not just on one cell, but I'm going to call it assemble on cell range. And it's going to take two arguments, begin and end, both of which are cell iterators or active cell iterators. And it's going to, this function is going to iterate on all of the cells in the range given by begin and end. So this is not the very first and the last cell, but let's say a subrange. And then in the assemble system function, what I'm going to do is I'm going to have a vector of pairs of cell iterators. And there's a function that is called threads : split range that is going to take the range from the very first to the one past the end cell, all the active cells, and is going to split it into a certain number of subranges of equal length, or as best as possible. And the number that I'm going to choose is the number of virtual cores. So let's say on my laptop, which has one processor, 4 cores, and for each core 2 virtual cores, then this number would be 8 here. That's the total number of virtual cores. And what I'm going to do, let's say if I have 100,000 cells, I'm going to split this range from cell 0 to 99,999 into 8 almost equal ranges. That is what this thing does, and it puts it into this variable subranges that is a vector of pairs. And then I'm going to have a loop not over all the cells anymore, but over all of the virtual cores. And for each one of these elements of this loop, I'm going to create a new thread that calls this function assemble on cell range with the first and the last element, or the first and the one past the last element of these subranges. And the index here should not be I, but it should be the T. The result is the thread that I'm going to put into a thread group. So that is, you can think of this as a collection of threads, and plus equal just adds it to the collection. And then at the end of this loop, I'm just going to wait for all of these threads to finish. So what I've done here is, let's say if I have 8 cores, then I will have created 8 threads, each of which will assemble on 1/8 of the set of cells. So that's a more efficient way than creating 100,000 threads. In particular, it only creates exactly as many threads as there are cores. And because they all have the same number of cells, they should all be running roughly the same amount of time. This can work. The problems that we have with this one is that, again, it does not really play that nicely with nested parallelism. If I had called the function assemble system in parallel with something else that also, for example, wanted to create 8 threads, then I have just created 16 threads, even though I only have 8 virtual cores in my system. And I have, again, over-allocated the resources that I have. The bigger problem is something that we call synchronization. So this function might look like it might work, But if you think about this a little bit harder, it turns out that it's actually not that easy. You need to do something that is called synchronization. And so let me show you in some detail what synchronization actually is. Because synchronization is one of the key concepts when you do parallelization on a single machine with shared memory. Synchronization refers to the following problem. So let's say, for example, I have two threads that are assembling currently on cell K and K prime. And you can, of course, think that there are many more threads if you want to. So let's say there could be threads 3 to 8. At the end of each assembly operation, we have to copy the local contribution into the global matrix. So if you go to step 4, for example, or step 3, you will find that at the end of the operations for every cell, we have a loop over all I, a loop over all j, and then we have something that doesn't quite use the syntax, but ultimately that's what it boils down to. Into the element of A, given by local DOF indices I and local DOF indices j, we will have to add to that the local matrix ij. Now, local matrix ij is a variable that is that only lives in the function for every thread. So local matrix here is a different object than local matrix over here. But the A, that's the global matrix. This A and this A here are exactly the same. And now imagine that by chance, at a particular time when we just execute these assemblies on cells K and K prime, that for whatever reason local DOF indices I on this cell K happens to be equal to local DOF indices I on the cell K prime as well. So let's say, for example, that these two cells that we're just assembling on are neighbors. Then I'm assembling on thread 1 here and on thread 2 over here. There's going to be two vertices that these two cells share on the interface. And let's say, for example, 42 and 108. This matrix here will contribute an entry to, or a contribution to the matrix entry A42, 108. This cell will do the same. So both of them actually want to write or want to add something to the very same memory location, right? Namely the entry A42, 108. And that's going to be a problem. We call this problem a race condition. So a race condition is, so here is just a summary of what I just said, right? So both of these want to write into entry A402, 108. Now, a race condition is something like this. So in order to execute this operation on thread 1, or on thread 2. What both of these threads will have to do is they read the entry A42, 108 from memory into the processor. They add their local contribution to let's say, the register where this variable is stored right now. And then they have to write the sum from the processor into this memory location again. And this is something that we call a race condition because what it means is that, well, if processor 1 and 2, for example, both read the same value at the same time, let's say, for example, we have not written into this entry yet. Both of these processors read 0. And then processor 1 adds 2.5. And processor 2, on its own processor, adds 5.5. Then processor 1 is going to write the 2.5 into the memory location. And then processor 2 is going to write its 5.5 into the memory location, overriding what processor 1 had just written. So the problem happened because the operation of adding something is not what we call atomic. An atomic operation is something that happens in one time instance, if you want to. That means that let's say processor 1 would read, add, and write at the same time. And so whenever processor 2 reads something, it would either read the previous value, immediately update it and add it, and then processor 1 would have added to that, or processor 1 gets to go first, immediately adds it instantly, and then whenever processor 2 does its operation, it would add it to the value that is already in this memory location. But that's not what this operation is. in reality, any floating point addition that we have on current processors is not atomic. That means that they first read, they do something on the processor. Maybe at that point the operating system decides to stop the thread and run a different thread, and then they add something, and finally they write it into memory. So there might be a long time delay between reading and writing, and the time delay between reading and writing is exactly what makes it possible for processor 2 to get into this picture and read a value that is not going to be current anymore. So what you get from this sort of thing is that the actual outcome of the program depends on the order in which these different threads execute their instructions. So to sum this up, a race condition is a situation where the result of a program depends on the relative timing of instructions of multiple threads. Race conditions can only happen if you have a read, modify, write sequence that is not atomic and that happens on the same memory location. And that's exactly what happened here with this entry A42108. If all the threads only ever read data, then there cannot be a race condition. Because in that case, if you read the same memory location twice and it is never modified, you will get the same result no matter which of the two threads get to read first. Right? Similarly, if the operation is atomic, so if we could, within one clock tick, for example, add to a location in memory without reading the data onto the processor, adding it there, writing it back, if we could do this, then either thread 1 would add to it first, or processor 2 would add to it first. But in either case, because it's an atomic operation, there is no potential for processor 1 and 2 reading the old value, at the same time adding something, and then one after the other reading whatever they have added to the old value instead of to the value that the other thread has just written. So if an operation is atomic, a race condition cannot happen. Finally, if of course different threads write into different memory locations, that's not a problem either. The problem with this is that it's very rare for operations to be atomic, and it's very rare for operations to only read data. I've showed you these three functions in setup system. These actually only read data from the DAF handler, and then they write into different memory locations. So there is no race condition here. There cannot be any race condition here. But for many other operations, in particular for ones that are embarrassingly parallel, you will always find these sort of race conditions, and we have to manage this somehow explicitly. So I would like to illustrate this to you with an example. I've written a little program that I can show you that demonstrates this problem with race conditions. So actually, let me use a different editor here. racecondition.cc. So view enlarge font. So what this program does is it adds up from, let's say it computes the sum from I equals 0 to n of the entries I squared. And it does this for n equals to, I think this was 100 million. Yes, 100 million. That is an operation that I think I could do in parallel, right? I could have two functions, for example, that the first one would add all the elements I squared for I equals 0 to n over 2, and the second function would add all the elements from I equals n over 2 to n. So what I'm going to do is I'm going to have two functions here, add first half and add second half, that add to a sum variable I times I. Both of these do the same thing. The sum variable here is initialized with 0 and is of type long unsigned int, because if I add all the squares of numbers up to 100 million, I cannot put them anymore in just a regular unsigned int, for example. Both of these functions here take a void pointer and return a void pointer, which is not material. This is just what the pthread create interface wants these functions to do. So I'm going to call in main pthread create with the address of this function add first half and add second half. And then it's going to initialize an object thread 1 and thread 2. And then these objects I can later use to say pthread join. So in main I need to wait for these these new threads to finish. And then I'm going to output the sum. And so let me show you what happens here when I run this. So when I run raceCondition.cc and I need to link with pthread, if I run this, I get an answer. And if I run it again, I get a different answer. If I run it a third time, I get a third different answer. So I could do this as often as I want. As often as you want to execute this program, it's going to just produce different numbers every time. And the reason is precisely the same as what we discussed in the slides before, that this operation here is not atomic. Every time we want to execute this, the processor is going to load this sum variable into the processor, is going to add I times I to it, and is going to write it back into memory. But both of these processors all the time read and write this data. And so typically what happens is that you read a value, and then you write it into memory, but in the meantime, the other processor has already read it as well, and is going to write something that is not I times I plus this value here, but plus the old value that it has just read. So this cannot work. This is not a good strategy, and we need to manage this. Obviously, not only are these results here all different, they're all wrong. Right? Not a single one of these is likely going to be the correct answer. So the way you deal with this is what we call synchronization. If you go back to the situation where race conditions can happen, it is always you read, modify, write sequences in a non-atomic way on the same memory location. And so there are multiple different ways how you can avoid race conditions. One would be you make the operations atomic. That means whenever you read, add, and write, you cannot allow another processor to read, modify, write at the same time. So the access to this piece of memory needs to be mutually exclusive. Whenever I am doing my read, modify, write operation on this piece of memory, no other processor is allowed to, or no other virtual core should be allowed to read, modify, write at the same time. That would be devastating for this particular program that I just showed you, because that's all these things do. But at the same, let's say for the assembly of linear systems, that may not be that bad, because typically processors compute all of these local contributions. That takes a long time, and then the actual read, modify, write operation on the global matrix is going to be only a very small part of the time. So maybe it's not that bad if a processor has to wait at that point until another processor has finished its read, modify, write operation. Anyway, so this making it atomic or making access mutually exclusive is typically done through a variable that we call a mutex, because it makes things mutually exclusive. Alternatives to this would be that each thread copies the global data structure and works on its own copy. For example, each one of these threads might add to its own copy of the global matrix, and then the mother thread later adds up the individual copies of this global matrix. And the final possibility would be that you split work by memory location. So for example, thread 1 would not be responsible for a certain set of cells, and thread 2 for a different set of cells, but each one of these threads would be responsible for all of the cells, but would only assemble on cells where the degrees of freedom are, let's say, between 1 and 10,000, and the next thread would be responsible for degrees of freedom 10,001 to 20,000, and so on and so forth. Because in that case, you would be writing into different parts of the memory, and that, again, cannot be a race condition. So I would like to show you the first and the last the first and the second way, in particular the mutex and the copy of the data structure. So before I do this, let me time this thing. So if you run this program, it's going to take approximately 0.2 seconds. Okay, actually, so it takes 0.2 seconds in real time, but it takes 0.4 seconds of CPU time. That's what this user thing here says. So 0 minutes, 0.4 seconds. That makes sense because I ran something on 2 threads. So if it takes 0.2 seconds in real time, it will take 0.4 seconds of CPU time. Now let me show you what the first way was a mutex. So a mutex you can think of as an object that at any given time only one thread can possess. So think of it as a token, let's say a coin. If I'm thread number 1 and I want to do my read, modify, write operation, then I can grab the coin and I can say, okay, as long as I hold on to this coin, I can do my read, modify, write operation, and at the end of this of the read, modify, write, I give back the coin. And then some other thread can come along and say, okay, well, I want to do my read, modify, write operation, but the coin isn't available right now, so I need to wait. Until finally the coin becomes available, in which case thread number 2 comes along, grabs the coin, does its read, modify, write operation, and then puts it back into the pool. So with this sort of analogy where you have an object that only one thread at a time can own, you can easily imagine how we can write a program that makes sure that only one thread at a time does its read, modify, write operation. And if only one can do this, then it's as good as if it was atomic. So if I wanted to write this kind of code, it turns out that the latest C++ 2011 standard actually has a header file called mutex, and I got a data type called std::mutex. So I'm going to introduce a variable that I call SumGuard. And now in this loop, what I'm going to do is I'm going to say SumGuard.lock that corresponds to grabbing the coin, or let's say waiting until the coin is available, and when it is available, grabbing it. Okay. When I have it, then I can do my read, modify, write operation, and at the end of this, I'm going to release the token again. And the second half thread is going to do exactly the same sort of operation. So let me show you how this now works. So I'm going to run this. I need to say that I want to use the C++ 2011 standard, and the program is called race condition mutex. So let me run this and see what happens now. Remember, the output here was different every time, okay? And it took 0.2 seconds and 0.4 seconds of runtime. So you can already see this is apparently taking a lot longer than 0.2 seconds. It took me 10 seconds and actually just 13 seconds of CPU time. So the amount of CPU time that I burned is not exactly twice as long as the runtime. But I got an answer, and if I run this again, you will see that the answer is going to be the same every time, and I think in this case I can actually trust that it's the correct answer. So let's see again here. Okay, so you see up to the last digit, the number is exactly the same, and I can repeat this. So I've just managed to make my program what we call thread safe, that it will produce the same answer every time. There is no race condition anymore. Of course, the price I paid is that it's going to take 10 seconds, when before, if I had just called the function's first half and second half consecutively, it would have taken me 0.4 seconds. So the message to take away from this is that it turns out to be surprisingly expensive to acquire and release a mutex, because it is something that the operating system has to communicate between different threads, between different processors. So a mutex is not a cheap data type, but it can be used for this sort of operation. The alternative was the third way that I had told you, namely to duplicate data. And let me show you this here. So The alternative was that every one of these two threads has their own sum variable. So I'm going to have two variables that I'm not calling sum, but partial sum. I initialize them with 0 here. And this function add first half is going to add into partial sums 0, and the second function is going to add into partial sums 1. And again, because we're writing into different memory locations here, there is no risk of a race condition. Now what I need to do, of course, is that at the very bottom here in main, the mother thread that has created these two, after waiting for these two threads to finish, is going to add the individual contributions of these matrices, or so not of these matrices, of these sum variables. Okay, so let me show you this. If I compile my program again, I'm going to run it. So what you see is that the output of this program is exactly the same as the one with the mutex, which we had just convinced ourselves is correct. And it takes 0.2 seconds in real time and 0.4 seconds of CPU time, which is, of course, exactly the time it has cost me in the original version of the program, except that now I actually get the correct answer. Okay? So you see how you can play with these different strategies to avoid a race condition. Certainly, the duplication is the preferred approach because we don't have to provide a mutex, for example. The downside, of course, is if you did this, for example, for the matrix assembly. Let's say I have a machine with 64 cores and I want to run 64 threads. Then the problem is that I have to have 64 copies of the matrix. That's going to be a huge amount of memory that I need to provide. And at the end, I will have to add all these 64 together into one. And that's going to certainly take some time as well. So this is always a trade-off, right? You can typically solve a problem by throwing more memory at it or more CPU time. So more memory would be the duplication, more CPU time would be the mutex. It's a trade-off which one of these two you want to use. Okay, so let me move on here. So I pointed this out, that when you use the strategy 1 with the mutex, that you introduce a sequential part, namely the writing part, where only one thread can work at a time. That contributes to the sequential component of Amdahl's law, and you will not be able to expect too much speed up in that case. Okay, so to sum this up, explicit threads means that you have to, the basic premise is that you keep large data structures only once, and you split the work on these data structures into multiple threads that can all access the same pieces of data. And then the operating system will schedule the threads to the actual CPU units. The goals must be that we have a number of threads that equals the number of cores, that in all phases of our program we use threads, and all threads work all the time. That is not feasible. It's hard to control, like I showed you, the number of threads because you might have multiple levels of parallelism. It does require synchronization, and synchronization always triggers Amdahl's law. So threads is sort of a concept that is nice in theory, but is hard to do in practice. So the experience of when you use threads is that basically it's a too low level description of the problem. You have to match the number of threads to virtual cores. It requires synchronization. It's hard to parallelize all of the operations. So for example, a linear solver is hard to parallelize. And a better approach to this would be that what I'm going to show you next, where we do not try to describe how to do things with threads, but where we describe what should be done. So we call this tasks, and it's a high-level programming interface. So deal.II has moved from threads to tasks over the years, and what I would like to do for the last few minutes of this lecture is that I introduce you to the concept of tasks, because it's actually fairly elegant. So let me come back to this example here. When you have this function setup system, we had this call to distribute the UFs, and then these three that depend on it. And let me add another one where I say constraints.condense sparsity pattern. So in this case, we have the following dependencies. Step number 1 can only run when we start this function. Step number 2 can run when 1 is done. Step 3 can run when 1 is done. Step 4 can run when 1 is done. Step 5 can run when we have built both the hanging node constraints and the sparsity pattern. So I can write this in the following way, that 1 depends on start, 2, 3, and 4 all depend on 1, 5 depends on 3 and 2, and to exit the function I need to be finished with steps 4 and 5. And this is typically represented in a graph that would look like this. And if you think hard enough about this, you find that this graph is always acyclic and directed, so we call this a directed acyclic graph, or for short, DAG. Everybody just calls it a DAG. So if you think about this enough, then what you will find is that every instruction sequence can be represented by a DAG. In practice, that's too low level. If I have, for example, let's say a sequence I equals 1 plus plus I plus plus j, then I plus plus I depends on I equals 1, plus plus j could be run in parallel to either of these two. I can represent this as a DAG. That is too low level. I'm trying to think of, let's say, every node of this graph as being some significant part of the computation. So how do you deal with a DAG? I can represent this in terms of two lists, essentially. So I'm going to have a list with all of the nodes in the beginning, and I call them non-ready nodes. And so let's say if I enter start here, okay, so if this function is entered, then that means that 1 is ready to be executed. So I'm going to be, so if I'm here, if I have executed start, then 1 is ready, so I move it from the non-ready list into the ready list. When I have, when I'm done with 1, I'm going to delete 1 from the ready list, and I'm going to delete these 3 edges, and that means that 2, 3, and 4 that were previously in the non-ready list can be moved to the ready list. And similarly, when 2 and 3 are done, I remove them from the ready list, and that means I delete these edges, and 5 can move from the not ready list to the ready list, and so on and so forth. The way we can deal with this, or the way an operating system would deal with this, is that it says everything that's in the ready list can be executed on one of the cores. So let's say I have 100 nodes that are in the ready list, but I have only 4 cores. Well, it's going to take the first 4 objects in the first 4 tasks in the ready list, and is going to put them onto these cores, and is going to execute them. And when one of them is finished, then it will just take the next from the ready list and put it on a core. So it's always going to be executing exactly as many tasks as there are cores, as long as the ready list, of course, is full enough. So this is one way where if we describe things in terms of tasks, things that need to be done, I'm able to map this to exactly the same, so I have exactly as many tasks running as there are cores. And that is independent of, let's say, the number of levels of parallelism that I have. I can always achieve this. So in deal.II, we support this sort of thing. I could do something like this. So I'm going to say threads, : new task, the object, the function that I want to execute on this object. Then that gives me a task number 1. And this is not quite the syntax that we have, but you could think of it this way, that I say t1.enqueue. That means the new task depends on t1, and it can execute after t1. This thing here, make sparsity pattern, can also run after 1. Interpolate boundary values can also run after 1. Constraints.condense can run after 2 and 3, and it returns an object t5, and then I can join these things again. And like I said, what I'm doing here is I'm describing what needs to be done. I'm not describing how it needs to be done. Right? I leave it up to the operating system or some other kind of scheduler to match the tasks that need to be done to the actual available compute resources. That's a much more elegant way of making sure that I have only as many things running as I have cores. So why tasks instead of thread? Like I said, it allows me to manage the number of threads, or it allows me not to manage the operating system, where some scheduler does this. I don't need to explicitly manage it. I get a number of running threads that is always appropriate, and it is relatively easy to describe dependencies. I also don't need the overhead of creating and destroying threads. The schedulers are able to just create, let's say, 8 threads at the beginning of my program, if I have 8 cores, and then on every thread, whenever a task is done, it just fetches the next element from the ready queue. Okay, so let me show you a second example here. When I think about the embarrassingly parallel tasks of assembly, then what I could do is, this should not be new thread, this should be new task here. So in the assembly system, I would just create, for example, 100,000 new tasks. And then they will be mapped to my 8 available cores, for example. This might not be the most efficient way to do it, but I can at least in principle do it this way. The problem, of course, is that I still need to synchronize the copy local to global operation. And one way to achieve this would be through something that we call the workstream class. So in deal.II, there's a class that is called workstream. The way it works is essentially like this, that we split this assemble on one cell into 2 parts, namely the computation of the local matrix and the copying the local matrix into the global one. I'm going to create one task for each one of these 2 kinds. For every one of these, let's say 100,000 cells, so I get 200,000 tasks. But the trick is that I'm going to tell the scheduler that it can run only one copy local to global task at any given time. It can run as many local assemble tasks as it wants at any given time, but only one copy local to global. And because it can run only one copy local to global task, there is no contention for this memory location anymore. So I don't need to explicitly synchronize things with a mutex, for example. It automatically works. So just by virtue of telling the scheduler that it can run only one of this kind at a time. Workstream also does some other trick, namely instead of creating tasks for all 100,000 cells in the beginning at once and creating an enormously long list of not ready nodes, or actually of ready nodes, it creates these tasks on the fly. Every time the ready queue runs low, it's going to create new tasks. And by this way, we keep the list relatively short. This is implemented in the workstream class, and workstream is used throughout deal.II, in particular in the assembly, in data out, and Kelly error estimator, and so on and so forth. So to sum this up, what you will find is explicit threads is sort of a clumsy way of doing things. It's how we did it until a few years ago, because that's all that was available. But ultimately, threads are too hard to manage, and it's a lot easier if we use tasks. If we use tasks, the scheduler can do a lot of the work that we need to do. We can avoid some of the explicit synchronization, and it provides a higher level interface. Now, one of the things that you will find if you do parallelize is that it's going to be very difficult to parallelize all operations of a program. And so that contributes to the sequential part of Amdahl's law. If you go through a program, typically there are certain things that are easy, like assembly, maybe part of the linear system solves. Some other parts, like creating a triangulation, is something that is very, very difficult to parallelize. If you want more information on this, so this is just, let's say, a global overview of the sort of things that that can be done and that you need to watch out for when you want to parallelize on shared memory. There is a very long documentation module in the deal.II documentation that talks about parallel computing with multiple processors accessing shared memory. It's worth reading through this. It describes a lot of the design of the workstream class in particular. There are also functions in the namespace parallel that show how to parallelize, let's say, short loops, like an L2 norm, for example. And then furthermore, there's a number of tutorial programs that talk about some of these concepts in actual programs where you can see how it's being used. I think with this, I'll leave this topic, and in the next class I come back to talking about parallelization on a cluster of machines where different machines do not have access to the same memory space but have their own memory spaces. And we then deal with this with a library that is called MPI for message passing interface. I'm going to show you, let's say, how you think about these sort of problems. But for now, this is how shared memory parallelism works, at least in principle.